Hi, and welcome to this VIP preview session of Guillotines, Sat-Nav, and the Query Optimiser, my session for Data Scotland. This is a preview session, so hopefully it's not going to change too much from the final product, so to speak, but that all depends on feedback. I've been busy in changing bits and pieces, but hopefully now the format is there. As Brentazar suggested, the first screen contains the session abstract and who I am and my Twitter handle, just so that people know that they are in the right place. So I guess I'm going to imagine that everybody is sat down and off we go. So this session is essentially all about opening up the query optimizer. It's what I consider to be a underrated part of SQL Server. We all throw queries at it. It does what it does. And just gets on with things. We don't often get the chance to really open it up and see how it works, and that's why I came up with the idea for this particular session. So today we're going to look at what the query optimizer is and what it does. We're going to look into how the optimizer works. So that's taking a bit of a dive into optimization phases, stages, and transformation rules. We're going to look along the way at some of the performance aspects of the query optimizer. We're going to explore some of the information that we can extract from the optimizer via dynamic management views and trace flags. And we're going to look at how we can influence the optimizer, and perhaps most interestingly, we're going to try and break it as well. Why would we do this session? Well, at the end of it, because we have an understanding of how the optimizer works, then we should be able to better assess our queries and optimizer performance. That should help us to write better queries. We're going to look at some of the design considerations so we can improve the design of our databases to help the optimizer, and perhaps more importantly than anything else, we're going to expand our knowledge on guillotines too. Now, a little bit about me on a slide entitled Who the Heck is This Guy? My name's David Alcock. I'm the Principal Consultant for DTA IT Consultancy. We're a small consultancy that specialises in building and optimising data platforms, specifically around SQL Server. I started out many moons ago as a VB6 developer, moved through various roles, Dev BI and DBA, before finally settling on a generic sort of title of data professional. And an important thing to know about me is I'm absolutely terrible at PowerPoint. So I don't know if you've seen this design ideas button that you can just press and it'll do it all for you. I use that all the time. It does do some random things. For example, for that particular section, it's decided to put an icon of a roast chicken or turkey. I've no idea why it did that. Another slide about me, and I can see already a few people have sort of clicked their fingers and thought, yeah, that's where I recognise that guy from. It's true. I'm also the Hood, the arch nemesis of the Thunderbirds. That's a role that I'm equally passionate about, same as SQL Server, not least for the funky outfits that I get to wear. Unfortunately, I'm dressed down today, with it being casual day. And another thing about me is that I use bribery, although I've crossed that word out because it is a pretty evil word. I use generosity for good feedback, so I often bring with me sweets and chocolates and pass those around so that you don't forget how generous or evil I actually am. So please, I'm going to imagine that I'm passing them all around, but actually it's a preview session, so I can just sit there and eat them. So I thought I'd start off with a little bit of an icebreaker. Other sessions have included little sort of games at the beginning of them. I don't know if you've seen Paul Andrews' Azure Icon game. I thought I would do the same thing, and it's a game fun for all the family, I like to think, titled Fun Facts About Guillotines. So what I'll do is I'll ask a few questions about guillotines. If you know the answers or would like to hazard a guess, then please shout the answers out. We'll see how how well you know guillotines. Just be wary that if you know all the answers, then the people next to you might want to start sort of inching away from them. I should be careful saying that because I did the session at a user group once, and one guy knew all the answers. So we'll go straight in. When was the guillotine invented? Anyone hazard a guess? Which is odd because there's only me in the room and I know all the answers. But hey, let's. Yes, yeah, good guess. It was actually invented in 1789 by a chap called, and excuse my French pronunciations, but Dr. Joseph Ignace Guillotin. Bonus information slide. He invented it because he wanted to design a more humane method of execution. So he oversaw the development of the first prototype, but it was actually designed by a doctor, Antoine Louis, and rather randomly, it was built by a German harpsichord maker named Tobias Schmidt. When did it claim its first victim? 1792. Correct. When was the last public execution by guillotine in Western Europe? See if anyone knows. The actual answer is 1977, the year I was born. In case you wanted to know anything else about me, when was it finally abolished? Yes, it was the last execution in 1977. It took them 4 years to decide to actually get rid of it. A bit of a longer question. Which future celebrity was present in the crowd for the penultimate public execution? This was actually in 1939. This public execution was banned until 1977. And the answer is Christopher Lee. So from now on, I hope you, as I do, refer to the query execution engine as Christopher Lee. He looks a little bit like that. Pretty scary looking chap. Did you know? Historically, the guillotine wasn't the default option for execution. Again, PowerPoint's doing its thing there and chose dinner time, which is quite worrying. Instead, the guillotine tended to be used for those who offered the executioner a handful of silver for a speedier and a non-botched execution. And to seamlessly link guillotines and SQL Server, providing speedier execution for our queries is exactly what the query optimizer is designed to do. You would not believe the sense of relief that I have in actually linking those together. And yeah, there we go. So the query optimizer, it's designed to make our queries faster. So to understand how it works, first of all, we have to take a quick look at TSQL or T-SQL, however you pronounce it. And TSQL is what we call a declarative language, and that means it's not an imperative language. So the difference is that an imperative language, they use an approach that exactly follows the logic that's stated in the code, as I've put there. In other words, they do exactly as they're told. The code follows exactly how we've put it. TSQL works differently as the engine determines the best way to return the results that we've asked for in the form of an execution plan. In a similar way, and this really helps with the session title, it works a little like Sat-Nav. So if you imagine you key in the result that you want in Sat-Nav, you put in your destination, and it decides the best way to get there. In very similar way that we ask for our results in the form of a query, and the query optimizer will determine the best way to get these results. So this is a diagram of query processing in the Query Processing Architecture Guide on Microsoft.com. It actually makes me quite mad because here we've got a query and we've got a database schema, and it's essentially saying that the query optimizer is 2 cogs, and that's what comes, and a query plan is what comes from it. It's actually a little bit more involved than that, and the query optimizer has got several phases. The first two we're not going to focus on too much today, but parsing and binding. Parsing is going to check the syntax. Binding is going to essentially produce a logical tree that it passes to the optimizer, and then the optimizer has a few tricks up his sleeve to get the speediest execution of our query. So there is a phase called simplification, the trivial plan phase, and then finally full optimization. So simplification, Its function really is that the optimizer will perform rewrites of the logical tree to simplify the query for optimization. So essentially, yeah, it's going to make the query as simple as possible for itself, so it doesn't have to work too hard. And this is really where it starts doing its magic under the hood. We don't ask it to do any of this; it just does it for us. So some of the tricks that it has, it's got subquery conversion. It'll take queries, it'll take subqueries and convert those into joins. We then have join elimination. So if the optimizer can tell that a join isn't needed, it just won't join the tables together. Contradiction removal. And I'll demo this in a second, and predicate pushdown and more. So this is the first little demo that I've got in Management Studio, which I'll just jump to and choose the right query. Simplification. So we're going to have a look at a couple of execution plans and things like that. I always feel like when I sit down in front of the keyboard, I should sort of play the piano or something. But hey, so the first one, subquery to join, we'll actually make sure that include execution plan is switched on. And here we go. So here we've got a few operators, and actually here we've got a join. Now, if we rewrite the query to actually have a join rather than the subquery, the plans will look exactly the same. So if I run them both, execution plan, there's our top query, there's our second query, and they look exactly the same. That's because essentially the optimizer is doing the same thing. Predicate pushdown, we've got a query here with a predicate business identity ID rather equals 10. In the execution plan, we don't see a filter operator after the join. Actually, what the optimizer has done is it's pushed the predicate down onto the index seeks. So it's far more efficient for this query to perform this filter or this predicate filter on the index seeks rather than sort of do the join and then perform the filtering after then. Join elimination. So here we have a query joining on two tables. Notice that we're just selecting from the human resources employee table here. Because of the referential integrity that's involved, it knows that it doesn't have to perform that join at all in the execution plan. Now, if I then select columns from that second table and run the query again and have a look at the execution plan, this time we get the join. So the optimizer very, very quickly. It's important to note as well, we've not even gone into that full optimization phase yet. These are simplifications that it's doing before anything else. So contradictions, I've got two forms here. So a value contradiction. So I'm going to select from this table where the sick leave hours is less than 5 and the sick leave hours is greater than 20. Of course, that's actually impossible. When I run the query, we don't actually get any results back, of course, and we just get a constant scan. Now, if I try the same thing with a primary key, and what do we think is going to happen? So this time we actually get a clustered index seek. So with primary keys, this form of value contradiction doesn't happen, and that's very much by design. So a contradiction based on a key column, a column with a constraint. So this time we're taking a look, select star from human resources where vacation hours is greater than 300. There's no records in there. It's done the clustered index scan. Now I'm going to recreate a constraint on this vacation hours so that it has to be less than or equal to 240. If I recreate that object, then rerun the query, so this time just a constant scan again. So that constraint has actually forced the optimizer down a much simpler query route because it contradicts the rule. So there are integrity objects within SQL, like keys and constraints, that actually directly affect the performance of the query optimizer. Back to the session, that simplification done. Is everybody happy with that? Yeah, cool. The next one, trivial plan optimization. If there's one or most likely one obvious way to execute a query, then the engine will use what's known as trivial plan optimization. If a trivial plan is used, the expense of full optimization is avoided. It's only used for very simple and straightforward queries, and the optimization level, trivial or full, is available in the execution plan properties. Again, I've got a demo here to show you some of the types of queries and whether the optimizer is going to choose a trivial plan or go into full optimization. And again, we can play another game if we like, and we can shout out the answers. So again, we'll choose to include our actual execution plans. We'll run that, select star from person dot person. Do we think that's going to be trivial or full? Let's have a look. And in here, our optimization level is trivial because it's got one obvious way to do that. Next up, if we've got a predicate where last name equals Maya, what do we expect? Trivial or full? And this time, trivial plan, so predicates don't actually affect. So this time we've got a like statement, so similar to the last query. However, we're looking where it contains the starting string value of my and then percent. Do we think this is trivial or full? Yep, again, trivial, so like. Okay, inequality predicate. So this time select first name, last name from person.person where last name doesn't equal Maya. And if we go into there, this time we have gone into the full optimization phase. So yes, an inequality predicate is one of the things that will result in the optimizer not choosing a trivial plan. Simple select star with a predicate. This time we're looking on the first name field. Yep, this time we have a full optimization level. This time is because there is actually no index on first name. So SQL servers had to have a little bit of a think about it. We've also got a key lookup because of the select star. So, and our key lookup, yeah, will contain all the other columns. This time we've got another query, select first name, last name from person.person, where first name equals Ken. This time, straightforward scan, but optimization level again is full. And again, we can see that it's weighed up the best way to do this, and it's actually picked an index on last name and first name. So really here, it's had to make a decision. And if it has to make a decision, there's no simple or straightforward way to get the data, then it's going to go into full optimization. This time, we're going to force the same non-clustered index that it's just used. What do we think is going to happen now? Trivial plan or full optimization? Let's have a look. This time we've gone into trivial. So the query is exactly the same, but this time it's actually limited by the hint. So there is only one way to actually do this query. So the decisions aren't there, so off it goes. So this time we're going to choose force a clustered index scan. We're going to choose a different column, and we're going to have a look at the cost. So let's have a run with this. Okay, so again, trivial plan. So again, chosen a different index completely. So if we have a look at the cost of this one, the estimated subtree cost is 2.84. And in our last query where we chose the index that the optimizer had chosen as well. So that's a key point. So we're picking the same one. Execution plan. Our cost is 0.10. If we go back and actually choose the one where we weren't influencing the optimizer at all with any query hints, forcing it down, any indexes, it's the same, 0.10. So the point is here that the query without hints or the one with a hint when it was using the same index, had a lower cost. And even though this particular query was a trivial plan, it has a higher cost. So the point that really I'm trying to make here is that cost doesn't really have any bearing on whether the optimizer will choose a trivial plan or a full optimization phase if it has to go into that. And finally, the last one, a join. And a join has chosen an index seek, and we've got full optimization, despite the cost being very, very low. So sort of to go over that last point again, this time, of course, there's many different ways that we can join tables together. So SQL Server, again, it has to make a decision. So it's gone into full optimization. Okay, back to the slides. What actually is this phase? So if we can't use a trivial plan, we go into the full optimization phase, and here is where the optimizer really does start to work. The optimizer produces a number of potential query plans, and they're known as candidate plans. So unlike Sat-Nav, which produces the fastest route to a destination, the query optimizer uses a cost-based decision to determine what is probably the best plan. There's two important points there. So the first is it's not just strictly cost, it is the lowest cost that's returned in the fastest time. And SQL Server does use an internal threshold for plan selection in these optimization stages. And then SQL Server does not assess every single possible plan. So it has to weigh up the time spent optimizing versus plan suitability. That's another reason why occasionally SQL Server might actually get it wrong. Shock horror, but it's true. So full optimization, so SQL Server has to think about a lot of things when we throw queries at it. It's got to look at the order to join tables, which heap or balance tree index should it use, how should it access the index, should it do a scan, should it do a seek, what physical join operators should I use, and should I use a serial or parallel plan. So they're just some of the decisions that it has to think about. If we take a really simple example, 3 tables with clustered indexes on each, and we wanted to join them all, SQL then has to look at the join order first, table 1 to 2, then 3, 1 to 3, then 2, or 2 to 3, then 1. It has to decide on the join transformations for each one. Should it do a nested loop, merge join, hash match? So just on join order and join type, we actually have 18 potential execution plans that it has to assess. And as well, the more complex that our queries are, the harder the optimizer has to work. That means that if the optimizer doesn't find a suitable plan in time, it's actually going to time out, and that's going to leave us with the best plan at that point. Now, optimizer timeouts. So by design, the optimizer has to return an execution plan, even if the plan is not as efficient as what it could be. So no matter what, it's going to return a plan. And it will use an internal timeout value that isn't strictly time-based, but is based on the number of transformations that it's looked at and includes the elapsed time as well. And if this condition is met, the optimizer stops and returns the best plan at that time. And we can actually see this in our execution plan properties under reason for early termination. So there's a quick image there where it's timed out. So a question is this a red flag? Despite the fact that I've used red color in there, not really. I think it certainly can be, because it's very indicative of perhaps an overly complex query. But the optimizer still does a very, very good job of optimizing. So even if it has timed out, the chances are, it's going to be still going to be pretty good. As I put there, the more overly complex the query, the more likely a timeout will occur. And a special note for nested objects. When I first went into front-end development, into database development many years ago, I would nest everything into views and store procedures and things like that. And they're very useful. These do add layers of complexity to our queries, and the optimizer can struggle with them. So it is something to look at. Have a look for timeout queries, and it may mean that your queries could be coded a little bit different. So if it doesn't time out, sorry, if it It'll then go through the optimization stages. So this is essentially what full optimization is. It contains 3 stages of its own. Stage 0, which is transaction processing. So this is where all the OLTP type optimizations are. Stage 1, which is known as quick plan, and then stage 2, which I think they just ran out of imagination at this point, coming to think of a name. So the third stage of full optimization is called full optimization. But hey, maybe they just thought, well, it kind of works. Each stage has certain criteria for entry and contains a specific set of transformation rules. So that's a good point. Queries don't just start at stage 0, some can start at stage 1, and each of the stages contain very, very specific transformation rules. I did check to see if there's a way that you can pull that out and get each one, but a guy called Paul White had wrote about that. I don't know if you've heard of him, SQL Kiwi, very clever guy, and he said you can, but it's very difficult. So I thought, right, I'll step away now. But what we do know is that stage 2 has all the rules. So that's got every single transformation stroke optimization trick up its sleeve is in that stage 2. Now we can actually query our optimizer information by using a DMV, exit query optimizer info, and we can also enable trace flags 3604 to get DBCC output into the message tab in Management Studio, and 8675, and this will return optimizer information into the messages tab as well. So I'm going to break out into a code demo and we'll take a look at some of those in action. Okay, so first off, just going to make sure that we're using the right database and that flags are off. They should be already. Okay. Going to turn on those trace flags. You can do it at the query level, but because I've got a fair few queries to go into, then we'll turn them off globally for now. Okay, so the first query, relatively simple. Just note that I actually will be recompiling all of the queries, because once it's gone into cache, then of course it doesn't need to go through these stages again. So forcing recompile forces it into the optimizer. So there's our query results, and if we have a look in the messages, so here's what SQL Server has been doing. So we have the simplification phase. We then have exploration tasks, which I'm not really covered in this one, but we'll sort of briefly cover in the transformation rules when we get to the next bit. And we can see here that it's gone straight into search 1. So this is our optimization phase 1. So if you remember, it did start at 0. The reason it hasn't gone into that is that there is criteria for entry on search 0 that the query has to contain at least 3 tables. So in ours, we've only got the 1 table. So it has no need to that. It's gone through all the different tasks, and then our final cost that we have here, 0.006, and that relates to the subtree cost of our query. So that's a quick look at the query level optimization that we can get just after execution. But actually, we can get instance level optimizer information out of SQL Server from the DM exec query optimizer info DMV. Lots and lots and lots of useful information in here. We got 39 rows, so I'll just run some with some filters in there. So for example, I can have a look here how many instance statements have been ran, delete, update, merge. Keeps all of these. One of the questions I was asked, if we drop the procedure cache, does it reset these values? No, it doesn't. No, these will only reset on a restart of SQL Server. Pretty useful. So let's start where the counter is like hint. So we can keep an eye on how many queries are being used for hints. So if you have a bit of a dislike about those, you can keep track on them. So just to test that, what we've got here is 33 hints. We'll run this query again, seeing that I've got an index hint in there. Run our query again, and we've gone up to 34. So that's the particular query in action. Again, instance level, and this means that SQL Server to date, since its last restart, has performed 749 optimizations. So they're individual ones, so that's going to keep on going up when queries are going to go up. We can actually break that down a little bit more so we can see the different optimization phases that are being used by my instance. So that could be interesting to compare sort of trivial plans, and on mine, none of my queries have gone into search 2, so we can say that they're not too complex. They haven't had to use the full optimization phase of full optimization. And again, we can just make sure that those numbers are incrementing correctly, and trivial plan has gone up to 240. Okay, so we can also see, and we mentioned these earlier on, Optimiser timeouts. So at the moment, my query optimizer during optimization has timed out 14 times. I did steal this query from Grant Ritchie. In fact, definitely check out his execution plans book. You can buy a copy or you can download a free PDF of that. Very, very useful book. It's got a query in there to force a timeout. So we can just say the timeout is at 14. We're just going to run this query, get the execution plan just to make sure that it's timed out. Optimization level full. Reason for early termination, it has timed out. We can see that it's using again these nested objects, so it doesn't actually look like an overly complex query, but yeah, the optimizer has timed out. And then if we take a look, we can actually see the optimizer has timed out. So it's gone in at search 0 because of the tables involved. The cost in that phase, 2.17892, that hasn't changed because it's actually timed out in search 1, returned the best plan or the best cost at that time. And then now we can have a look if our counter is incremented, and that's gone up to 15. So we can keep an eye on those. So optimization is all about getting a gain. So that's one thing that we haven't really demonstrated yet. So we're going to have a look at this query, gain, have a look at the output. We're going to go straight to the end of search 0. We have a cost of 9.9600022. And then the cost at the end of search 1, so it's the OLTP phase, then our quick plan phase, and we've actually got a gain of 0.6. So there we can see that the optimizer doing what it's supposed to do, and it has decided at this point that that is a suitable cost for the query, and it's returned the execution plan at that point. And we can also take a look to see the average gains on our instance. Again, it's a bit of a cumulative value, but we can actually see that on mine, 6 occurrences where the optimizer has gained from going from stage 0 to stage 1. And again, we've never hit stage 2, but if that had happened from stage 1, then we'd see it in there. That's the optimization stages bit done. We're now going to jump a little bit deeper into transformation rules. And these are the individual optimizations that SQL Server applies to our query. They are based on relational algebra. Don't worry, we're not going to go flying into that. But they do use a pattern and a substitution. So what actually happens is that they will take a logical expression and they will generate equivalent alternatives. And we have logical alternatives in the exploration phases. Remember those earlier on. And if they are implementation, transformations, then they are classed as physical. So the perfect example would be a join. If we take a logical expression of a join, most of us will sort of write in a join, left join, outer join, etc. But the physical expression, what's actually happening in the optimizer, could be a hash match join, a nested loop join, or a merge join. Not many of us write queries like that. If we do, then we're either really clever or really scary. And there we can actually see the tooltip text of a hash match operator where we have the logical operation and the physical operation. So We can use query hints to disable rules. That's actually what happens when we use a hint. It doesn't sort of force just that, it actually disables the rules underneath. And the number of rules can change on version of SQL Server. So it's interesting to see, not just between sort of 2008 and 2017, but actually the difference from, say, a CTP release to a latest release of a production version. And we can use a DBCC statement, or we can go into the exec query transformation stats to view information on the rules. And a final note there is that whilst optimization is going on, the optimizer stores information in an internal structure called the memo for quick access. So we're on to the final demo, where we're going to have a look at transformation rules. Okay, so again, just making sure that trace flags are on. And DBCC show on rules. So this is returning to the messages tab all the rules that are currently switched on my instance of SQL Server. So we can see lots and lots of examples. Some of them, so we can see there, that's join to nested loop. And then other ones might be a little bit more difficult to sort of understand what it's actually doing. But there's all kinds of things in there. Probably an easier way to view the rules, and we actually get a little bit more information, is to use the DMV exec query transformation stat. The one thing that we don't get here is if the rule is switched on or off, and we'll have a look at that shortly. The two columns to focus on is promised, which is a value that determines how useful that particular transformation is, and succeeded is the amount of times that it is being used. So we can take a look and perform a filter to look at some of the ones that relate to joins, like in this example. So at the top there, we've got join to nested loop, join to sorted merge, and join to hash sort. So there are some of the familiar ones, but there are a lot more that relate to joins that are in there, quite a few transformations. And we can have a look at one in particular. So here we have got the hash match join, and we can see that on my system, there's been 582 occurrences of the hash match join. And we'll just have a look at this particular query. Again, I'll remember to switch on the actual execution plan. And we can see there, hash match join has been used. So if I go back to my query, we can see that that number is now at 584. So using that example again, so the optimizer has chosen by default to use a hash match join. So the optimizer has weighed up the statistics and thought, right, that's the best join. So what I can do is use the query rule off option, and I can actually turn off hash match joins for that statement. So which one do we think it will use in its place? And in this case, SQL's decided that the best available join option that it's got has got the merge join. And interestingly enough, in here, one thing I didn't mention, the query cost is now 0.041 on the hash join. Let's just take a look at the cost for that, 0.039. So we can see that that merge is not as efficient in terms of query cost. I don't just have to disable one transformation rule, I can disable a couple. So now I'm going to take out hash and merge join options. We'll run the query again. What do we think it's gone for this time? Yep, nested loop, and the query cost has now gone to 0.097. So that's quite a big jump up. So we can see there that the optimizer is choosing the best sort of option each time. What happens if I turn off hash match joins, merge joins, and nested loop joins? If we go for them all, it's actually going to choose a nested loop join. That's really interesting, because we have actually turned off the join to nested loop transformation. So I'm just going to run a query now to see exactly what it is doing in terms of joins. So this is a query that, again, I had a look at in a book that's online. So this is the Benjamin Navarro's book about inside the query optimizer. Again, you can get that as a free PDF. Very, very useful information. And this is just going to return account of any of the transformation rules that start JN that have changed before and after queries. So I'm going to run exactly the same query. And actually, we can see here that the transformation rule that it is used is not joined to NL because we turned it off, but it's actually used a transformation joined to index lookup instead. So I then thought, okay, so it's beaten us there, but what actually if I turn off the hash match join, but actually try a hash match hint in the query? What do we think is going to happen this time? And we'll give that a run, and actually we've got a bit of a shade of red there. Query processor could not produce a query plan because of hints defined in this query. So we can actually completely beat it if need be. So this time we just had a look in the difference in joins and to actually return the join transformations that the query was doing. And this time, let's just look at the query again, but have a look at all the different optimizations that it has gone through. So transformation rules. And this is it. So they're all the ones that it's used to produce our execution plan. The one thing that we haven't done is actually, apart from the joins, is have a look at the benefits of an optimization. So we're just going to run this query. We're going to focus on a aggregate push down before join optimization. So we'll just have a look at this query here. Have a look at the execution plan, so we can see that the stream aggregate has actually been pushed down into the query. We'll just have a look at the cost here, 0.30. And now I'm actually going to turn off the transformation rule that relates to that. So we're going to disable that optimization again, 0.30. If I run that query again, we can see that it's now moved to after the join instead of before the join before, and this particular query has gone up to 0.33. So there is a 10% gain in that query that it's produced. Now we've been focusing on turning off joins per query. I can actually turn that off on my entire instance if I want to. So there we go. I've used the dbcc command rule off, and it should add that these are undocumented commands, which is normally where all the best ones are. And I have turned off that transformation across my instance. So I'm going to run that query again, and there we go. It's dropped down to merge because it doesn't have that option at all. And we're going to turn that back on again in case I do some query work later and wonder why things aren't going wrong. Now, I did mention the memo briefly earlier, and as we've got time, we'll have a quick look. So we can use a trace flag 8608, and that's going to look at the initial memo. So this is what it looks like that SQL Server has been writing to. 8615 will show us our final memo. I might cover this in another session. The final memo should look a little bit more complicated and complex. And then finally, we'll turn off that traced flag. And that is the demos completed. So a whole bunch of stuff to take in. There are some takeaways in that to help the optimizer out. The first one is keep the engine up to date, because of course updates may give new features that lie really under the hood, new transformation rules that it can use. Use solid database design principles. I know there's lots of debate about foreign keys and things like that, but we have seen here that they can help the optimizer make some really good decisions. Keep queries as simple as possible. Absolutely. The more complex our queries are, the more harder the optimizer has to work, and if we go overly complex, it will time out. Check your queries. Always have a look at queries. Be looking for things like timeouts and inefficiencies, as we would. Queries do change as data changes, so keep an eye on those. Use query hints sparingly, and if you do, don't forget about them. So we've seen here that some hints can cause detrimental effects to the query optimizer, certainly turning off things like hash match joins across an entire instance. And again, because data changes, query changes, don't forget about your hints. Keep statistics up to date. I know we haven't covered them in this course, but that's a general piece of advice. Review workloads and queries, and that means make use of the query store. And of course, we are moving into an age of automated tuning, so definitely take advantage of those features. That is all for me. Thank you very much. If you have any questions, like why all my dogs decided to bark at the end, then please fire away. You can find me on Twitter at SQLSeeker77. You can look me up on LinkedIn. You can email me at david@dtaconsult.co.uk, and all my slides and scripts and pictures of me will be published to GitHub. And thank you very much to everybody, and a special mention to my wonderful mentor, who hopefully will be looking at this and not thinking that, oh my gosh, there's too much work to do. So I will speak to you soon. I will see you soon. I hope everybody is well, and thank you very much for your time.